Back to my channel. So in this video I am going to teach you about the magnetic field due to toroid. So in our last video already we have discussed about the solenoid. Actually this toroid is nothing but it is solenoid only, but that solenoid, if you take the two ends of that solenoid and bent and turned in the circular shape, then that is called as the toroid. So here I will give you the definition of toroid. So toroid means solenoid bent in circular shape. So if you take the solenoid and bend it in the circular shape, then it is called as the toroid. So construction of toroid means structure of toroid, how it appears means if you take one hollow circular ring like structure, hollow circular ring. So for that ring, if you wound the wire surrounding around that ring, then it appears like a toroid. So that is the structure of the toroid. Actually this toroid is also called as electromagnet, or else we will call it as artificial magnet, because whenever you pass current in that wire, it will create the magnetic field. So it is called as the artificial magnet because it acts like a magnet, or else you can also call it as electromagnet because by passing electricity it is creating the magnetic field. So by these two names we can call electromagnet or the artificial magnet. So now we will discuss about the toroid. Why we are studying this toroid means it is creating the magnetic field. So here in this toroid we are going to study three cases: one point inside the toroid, one point at the center of toroid, and one point outside the toroid. At all these 3 points what will be the magnetic field, and we will calculate that magnetic field with the help of the Ampere's circuit law. So let's start. So here I will draw one circular ring. So this is our circular ring. First I am making the solenoid, hollow circular ring. So this is our hollow circular ring. For on this hollow circular ring we will wound the wire as we have done in our solenoid. So like that wires are wounded. We are having n number of turns. So after that, in this wire we will pass the current by connecting the battery. So here we are passing the current in this wire. So like this current will flow in this toroid. These two ends are connected to battery, and this is the center of this toroid. And next we will take point P here. This is our point P, and this is our point Q, and this is our point S. At these 3 points we want to calculate magnetic field. P is the center of this toroid, S is inside the toroid, Q is outside the toroid. So if we want to find magnetic field using Ampere circuit law, then what we will do means we will draw one closed loop which is passing through the point P, means where we want to calculate magnetic field. So after that we will apply the Ampere circuit law. So now we will draw the loop. So first I will draw the loop for this point P. So this is the loop for point P, and this loop should be drawn in such a way that it should be symmetric in nature, that we have already studied. And one point we will draw for Q. This is the loop for the point Q, and next another one loop we will draw for S. So here we have drawn these 3 loops. All these 3 loops are called as the Ampere's loop. What we will call Ampere's loop. Why we draw Ampere's loop means to calculate the magnetic field using Ampere Circuit Law. So now we will study first case. In case 1 we will study center of toroid. Center of toroid at P. Now first we will find out magnetic field for this point P, which is center of this toroid. So for that we will apply Ampere Circuit Law, that is closed integral B dot dl is equals to mu naught I. So in this case, here inside this toroid there will be no magnetic field because there is no current present inside this toroid. Actually you see here, if this is our toroid, so here in this portion there will be no current. If there is no current means there will be no magnetic field. So here if I is equals to 0, then magnetic field B is also equals to 0, means closed integral B dot dl value will become 0. So here I will write closed integral B dot dl is equals to 0. Next second case we will study. So before going to study the second case, I will show you the structure. If you cut here, then it will become straight. So how it appears means like this. So already you have studied this in our solenoid. Means if you join these two ends in circular shape, it will become toroid. If you cut this toroid and if you make it straight, then it will becomes the solenoid. So these two are the toroid and the solenoid. Basic difference is it will be straight like tube like structure, and it is in circular shape. Both are same. In both cases we will generate the magnetic field. So next we will go for case 2. Case 2 is point outside the solenoid. We'll write outside toroid at Q. Again we will apply Ampere Circuit Law, that is closed integral B dot dl is equals to mu naught I. So in this case, this I is what we have to take the net current. So this is our point Q. Inside this, if you are observing, means this point will appears like dot and this point appears like a cross. Current is coming outward, going inward, coming outward, going inward, coming outward, going inward. So in all these cases, one current is coming outward and one current is going inward. So in this case, one current will take it as positive and the other current will take it as negative. If you take the total net current, then what happens means both will be cancelled, because one current is positive and the another current is negative, because one is coming outward and one is going inward. So for that, net current will become 0. This already we have studied, no? So like that, one current is inward and one current is outward, and here we have drawn the direction of magnetic field. We'll take this is the direction of magnetic field. Then what happens means we'll curl the fingers like this. So when you are curling the fingers, this thumb is pointing inward. So this inward current will becomes positive and this outward current will becomes the negative. So this is I1 and this is I2. So in this case, the net current will become 0. So here also same. For this point Q, what we are observing means one current is pointing outward, one current is going inward, one current is coming outward and again another is going inward. Means the net current in this case will be 0. If this I will become 0, then whole value means magnetic field will become 0. If I is equals to 0, then magnetic field is also 0. Therefore, closed integral B dot dl value we will get it as 0, because net current inside loop is 0. So next we will go for case 3. Case 3 is the important case because here only the magnetic field will be present. So we will take inside the toroid. Inside the toroid at S. So at this point, S point, we want to calculate magnetic field. So I will draw here one same toroid here. Here is our point S. Here this is the center. So this distance we will take it as R. So next, after that, here the current is coming outward and again here it is going inward. The same toroid if you draw like this, top view, then we can observe like this. One current is outward and one current is inward. So now for this this loop, this is our Ampere's loop. We will write here Ampere's loop. So for this we will apply the Ampere Circuit Law, that is closed integral B dot dl is equals to mu naught I. So now this can be written as closed integral B dl cos theta. Here theta value will be taken as 0 degree because this is the direction of the magnetic field and this is the direction of the current element. Both are in same direction, theta will become 0. So here we will take it as cos 0 degree is equals to mu naught I. Next, this can be written as closed integral B dl is equals to mu naught I. Next, B multiplied by closed integral of dl. If you want to calculate the total length of this loop, then it is a circle. So the length of the circle is called as circumference. So circumference of circle will be taken as 2 pi r equals to mu naught I. So this B can be written as mu naught into I divided by 2 pi r. So this is the magnetic field at this point S, but this is for only one loop, means for only one circular ring. Here we are having n number of turns. Wire is wounded, no, n number of turns. So here we have to add one n number of turns because in one loop, in one circular ring, it is carrying I amount of current. So like that, if we are having n number of turns, means this current is multiplied by n. Means total current can be calculated by total, means number of loops multiplied by the current. For example, here if this is one loop or one circular ring, so in this one circular ring I amount of current will be flowing. So like that we are having n number of turns. For this n number of turns, to calculate the total current, then we have to multiply this n number of turns by the current, then we will get the total amount of the current. So here this B can be written as, if there are n number of turns, if there are n number of turns, then I is equals to n into I, means the current can be multiplied by n times of the current. Therefore B is equals to mu naught n into I divided by 2 pi r. Mu naught n into I divided by 2 pi r. So now I will tell you what is ideal toroid. Ideal toroid. Ideal toroid means where the thickness should be very small as compared to the radius. So for example, if this is the diameter or the thickness, you can tell if this diameter is very less as compared to this radius. So here I will write, if d value is very small as compared to radius, then it is called as ideal toroid. Ideal toroids are like this. Means this thickness is very small as compared to the radius. Means this R value should be very high as compared to this diameter, then this type of toroid we will call it as the ideal toroid. So this is all about the toroid. Actually, magnetic field is present only inside the toroid, inside point P and outside point Q. In these two cases, magnetic field will be 0. So in next video we are going to study about the force between two current. Means one current and the other current both are in opposite direction. In that case, what will be the force? So stay tuned.